McGill NeuroTech, and this is IRiSSE. IRiSSE is a visual speller that allows people to communicate by looking at individual characters. Our speller consists of a keyboard where each character is flashing at a different frequency and a different phase, and the user simply has to look at one of the characters to select it. The way it works is through using an EEG signal called Steady-State Visually Evoked Potential, or SSVEP. When a person looks at a visual stimulus that is flashing at a specific frequency, the neurons in the visual areas of the brain, the occipital cortex, will be entrained at the same frequency. So for example, if our user is looking at the character A that is flashing at, say, 10 Hz, then the EEG signal that we measure from the back of the head will have higher activity, show higher activity at 10 Hz. Our keyboard has 31 characters in total. We have the 26 letters of the alphabet, the space, the backspace, and the numbers 1, 2, 3. The numbers are for our auto-completion feature, where we predict the top 3 most likely letters that the user is trying to spell. And this allows for faster communication overall.
Our work can potentially benefit people with reduced motor ability, which limits their ability to communicate with the outside world. That includes clinical populations whose neurological conditions limit their capacity to interact with the outside world. Our project will yield an affordable piece of technology that can assist their interactions with the computer keyboard and output their thoughts.
We collected data from 11 university students, both male and female, using an 8-electrode setup on the occipital lobe of the participants. The positions of the electrodes were informed by our literature review and based on the 1020 system. We ultimately chose to use the OZ, O1, O2, PO7, PO8, PO, PO3, and PO4 electrode placements. Data collection conditions were controlled for each participant by using the same electrode placements, positioning the participants 40 centimeters away from the screen, and using the same hardware and environmental conditions.
The data collection interface cued the participants to look at a specific key by highlighting it red. All keys would flash at their unique frequencies and phases for 5 seconds. We used frequencies from 6 to 12.9 Hz with a step of 0.23 Hz. For the phase, we started at 0 and it increased 5.35 high ratings. The data collected would be stored in the database and attributed to the key. This process iterated through each key on the keyboard, completing 1 block of data collection. We aim to acquire 10 to 15 blocks of data per participant.
Setting up wet electrodes on the occipital lobe naturally presented many challenges. The participants' hair in particular would cause the electrodes to move and fall off occasionally, causing long setup times and variable electrode placement. We decided to fix the electrodes in place using a headband that used the inion, nasion, and helices of the pinnae as landmarks, and this helped to reduce setup time and increase setup consistency across participants.
Noisy data was an additional challenge we faced. The environment was found to be the greatest culprit. We were able to limit noise to 8 microvolts for each electrode by limiting movement of the participant and of others in the vicinity.
So the task of a signal processing team is to take raw noisy EEG data and convert them into something sensible we can use to predict the data. So once we get the data from EEG, the first step is to clean the data by applying a notch filter to get rid of the 60 Hz electrical noise in the EEG. And then we could use a Chebyshev bandpass filter to isolate the range of frequency we're interested in. So we also spent some time tuning the hyperparameter of the filter and experimenting with other cleaning methods to get the purest signal as possible. So the next step is to figure out which of the flashing frequency best correlate with our measured EEG data. And this can be difficult because a lot of frequencies are very close to each other. And we also need to make sure that the frequency is low enough for the monitor to display and it's easier for user to perceive. And increasing the range of frequency and keep the highest frequency low makes this process easy. The clean signal is then passed to the CCA or canonical correlation analysis to figure out which flashing frequency correlates the best with the measured EEG data. It's also worth mentioning that CCA works really well because correlation is much more robust to short signal length and very small frequency gaps when compared with other related methods such as power spectrum density.
Many of our challenges stem from adapting existing techniques to our limited hardware. For example, we had a sampling rate bottleneck of 250 Hz compared to 1000 Hz in a lot of existing work, so this informed the techniques that we could use. Additionally, our EEG device had only 8 channels compared to 9 or more channels in most EEG devices. So our solution was to use a public data set to select the best 8 channels. We later reduced that to only 1 channel because it captured all of the informative features in the data. Another challenge was inference speed. Since long processing times can severely challenge the rate at which a user can type, we had to make sure that our algorithm could process the data quickly. These factors informed our choice of algorithm. CCS fast. It's a general method that's independent of the user. It doesn't require calibration, and it worked better in our setting. Once we find the most probable letter, we send it off to the software team.
The software team worked on 2 pages, the training platform, where we collect the EEG data for each key, and the inference platform, where we predict which key the subject is looking at.
So I will be talking about the data collection platform. The data collection platform is built using a React web app and a Python backend that collects data from an open BCI device. It is a system for the collection of time series data that handles both the networking, time synchronization, as well as it provides near real-time access, viewing, and recording of the data. The backend first starts by creating a shared queue so that it streams the data inside the shared queue, and this shared queue is shared across the whole backend so every sub-process can access it. This allows for easy communication between the backend and the open BCI device. After that, the stored data that is made available by the collection process is uploaded to a Postgres database. And overall, the platform is built on a layer of abstractions and successfully performs data collection.
The inference platform integrates the work of the machine learning and signal processing teams. The React web app dynamically generates a keyboard layout and collects the data for a certain period of time before hitting the backend endpoints to get the predicted letter and autocomplete recommendations. The main difficulty was with rendering the flashing keys. To get a high enough frame rate, we had to do some profiling optimization to get a smooth sinusoidal signal. And with that, the platform successfully integrates the language model and CCA algorithms to finally display the predicted character on the screen.
The machine learning subteam was tasked with creating a language model to speed up communication on our Stellar. We created an autocomplete feature that takes previously typed characters, and we autocomplete the word by the most likely words from our model. We also created the next word prediction model that takes the previous typed word and the typed characters of the word that wants to be completed, and the user will select the word with the most likely probability. We trained our model on the TV corpus dataset. This dataset contains British and American shows from the 1950s to 2018. This dataset allows our model to have a sense of a natural spoken language, and which is most likely what the user will want to communicate when spelling. One of the challenges our team has faced was when users misspelled words. So if a user had 2 characters that don't lead to any predicted words, our model accounts for the keys surrounding the key that they selected on the keyboard and is able to provide the next most likely words given the surrounding keys.